This is problem 3-162M. It's on page 177, and you should definitely refer to the figure in watching me solve this problem. We're trying to solve it yourself, of course. For the lever shown in figure P3-162, called a bell crank, compute the required diameter of the pin A if the load is repeated and the pin is made from C17200 beryllium copper hard. The loads are repeated many times. Now, when you look at this problem, and you see the pin area, there's no diameter given for the pin area. There are a couple of loads, and the loads that are given, I guess I'll have to sketch some of this to talk about it. Let me sketch the figure actually. I'll sketch not all the dimensions, but basically what this crank looks like. So there's a horizontal line this way, and force F1 comes off at a 30-degree angle. Force F2 comes off of horizontal at a 10-degree angle, and the pivot point A is up here. Now there's dimensions given. I won't copy down all those dimensions because we don't need them. Well, we do need them, but it would waste time to copy them all down. But what I wanted to do to solve this problem, first of all, there's a statics problem here. That is, how much load is applied at the pin. Well, we don't know how much load is F2, but we do know that F1 is 3.6 thousand newtons. Now, I don't think that this is something that's going to rotate and accelerate very, very fastly, so I don't think that there's much dynamic loading to be considered here. This is not a terribly large piece if you look at the overall dimensions. The dimensions are all on the order of tens of millimeters, so definitely less than 100 millimeters is not all that big. So I don't think there's any dynamic considerations going on here. And we can calculate F2 based on statics, and that should be close enough for what we're doing. So what I'm going to do is sum moments about A in order to compute the compute F2. Of course, we could sum moments about this point where F2 is applied and calculate the load at A directly, and that may have been a better way to go about it. I didn't do it that way. I didn't think of it when I did this. Here's what I did. I calculated the x component of F1 and found that it would be 3.6 kilonewtons, and I'm going to use my shorthand cosine 30 degrees. That comes out to about 3.1177 kilonewtons. F1y, 3.6 kilonewtons multiplied by the sine of 30 degrees gives us 1.8 kilonewtons. Now, notice that this force is to the right and this force is downward. Now, if I were to sum moments about A, I would have two unknown components in F2. So I went ahead and recognized that F2y over F2x is equal to the tangent of 10 degrees. So that's the relationship between the x and the y components of F2. Now I can sum moments about A. I'll take counterclockwise as positive. They should sum to 0. But let's take care of the F1s first. The x component, this component of F1, has a moment arm whose height, where's the figure? The height is 30 millimeters. So, also F1, that causes a negative, or F1x causes a negative, so negative F1x times 30 millimeters, that's the moment of the x component of F1. F1 has a negative y component, and so the distance here is 40 millimeters, and again that's a negative moment, so F1y times 40 millimeters. I'm not putting in the dimension units, or the dimension units, and the reason for that is they'll just end up canceling because I'm going to solve for forces from this, so it doesn't really matter. But notice F2 will also cause a moment about A. The x component will cause a positive moment, so we have F2x, and we need the distance from A down to F2. If you look at the figure, that distance is 25 millimeters. I'm checking myself as I go to make sure that I calculated this right. I have been known to make mistakes, and if you see any mistakes, please leave a comment below the video for it. Anyway, the y component is up, and notice it's to the left of A, and so it also is going to cause a negative moment. So we have to say minus F1y multiplied by the distance horizontally from A over to the point of application of force 2. Looks like that distance is 10 millimeters, and that is what I used here. Good. Okay, so now the thing to do is to solve for F2. So let's start off by putting all the F1 stuff on one side and simplifying things. If I move this to the other side, both of these negative signs will go away. I'll just pull the dimensions out front. F1x is this term, plus 40 F1y is this term, equals, just basically moving these to the other side, F2x, pulling the 25 out front, 25 F2x, plus, or well, no, it's still minus, 10, and F1, I'm sorry, I've got F1y here, this should be F2y, I made a mistake earlier, because it's the y component of F2. Anyway, F2y can be written in terms of F2x, because F2y is F2x tan 10 degrees. So I'll just make that substitution right here, F2x tan 10 degrees, and that takes care of this because that was the last piece of it. So the reason for making the substitution is so that the only unknown is F2x. I've got all the equations together now, and I can solve for the unknown force. F2x, or at least the x component of it, is 30 times F1x plus 40 times F1y, repeating the left-hand side of the equation, divided by the factors around F2x. That's just 25 here, minus 10 tan 10 degrees. So this 10 and this 25 have units of millimeters, like the 30 and the 40. F1x is known here, F1y is known there. Notice I don't need to add any negative signs to this because I've already taken the direction into account. I won't go through the gory details of plugging in the numbers. You can plug this in your calculator. I got about 7.1237 kilonewtons, which makes sense. The distance from 2 to A is less than the distance from A to 1. I would expect any component, especially the horizontal component that's almost all of F2, I would expect it to be quite a bit above this. In fact, it's about twice. So that makes sense. So F2y then can be calculated just from this equation. That's the easiest way. So we'll just take this number and multiply it by the tan of 10 degrees. When you do that, you get about 1.2561 kilonewtons. So there's the force 2. We could calculate the magnitude of it, but there's no need. I just realized that the vector sum of these two forces is equal and opposite to the force at A. So that's what I did next, was I calculated the pin force. So a force something like this, P, would be applied to the slot or to the hole, which would be equal and opposite applied to the pin. Anyway, so calculating the pin force P, it would be the square root. Let's see, I need the x components of F1 and F2 added together. So that's F1x plus F2x. Now I'm doing a vector sum with the y components, so I'll have to add those, square them, add the y components squared, and then square root to get the vector sum. But you'll notice that the y component of F2 is opposite in direction from F1. And so I just need a negative sign there. So F1 has a negative component. I'll just put the negative sign there. It doesn't really matter where you put it. And that should complete the equation, because now we've got a negative component in the y direction for F1, positive component for F2, basically just taking the difference between those magnitudes, squaring it, and this should give me the vector sum. So you've got all the numbers. Here's F2y, here's F2x, you've got F1y, F1x, plug them all in, and you'll find that the force applied to the pin is about 10.2558 thousand newtons. So that was a lot of statics work just to find out how much force was applied to the pin. 10.2558 kilonewtons. So now that we've finished that part of the problem, we're going to erase all of this work because we don't need it anymore. So now we finally get into strength of materials. Now, in looking at this problem, when I first looked at it, I was a little bit confused. I hadn't really noticed the section, and I just thought, oh, this is an interesting combined loading problem, or, well, two different areas to analyze, basically. Notice they did not give us the thickness of this link, and so I thought, well, I could size the diameter based on shear, and then I could size the thickness based on bearing stress. Well, they didn't ask for bearing stress, but I went ahead and did it anyway. So let's go through the shearing part first. So basically, if the pin's here, it's how much diameter do we need to keep from just shearing it off is the question. And so what I did is I just decided, well, the area would be pi over 4d squared. And I'm going to use a design stress of the yield strength over 8. Now, you have to be a little bit careful with this. Let's talk about this for a minute because this is a very important point. If you look up the percent elongation of this particular material, what you'll find is that it's only 4%, which means that we classify it as brittle. And then on page 154 in the book, your author talks about this just a little bit. He talks about brittle materials in shear. I think it's 154. Let me find it. I've written down a page number. Let's see. 159. I misread my own writing. Okay, let's try that. Here we go, page 159. If you'll notice, there's a section in the center of this page that talks about brittle materials. It says, design shear stresses for brittle materials are based on the ultimate strength in shear because they do not exhibit yielding. A higher design factor should be used than for ductile materials because the materials are often less consistent in structure. However, published data on acceptable design factors are lacking. It is recommended that testing be performed on actual prototypes of shear-loaded members made from brittle materials. So I thought, well, since we've got this beryllium copper, what properties does it have? Well, if you look it up, you'll find that the ultimate strength, let's see, the material is C17200. The material has an ultimate strength of 1,344 megapascals, but it has a listed yield strength. The listed yield strength is a gigapascal, so 1,000 megapascals. Now it also, like I said, has that 4% elongation, which indicates that it's brittle. So what should we do here? Well, there's some more information in your book on the, let's see, I think it's the same page. Yeah, here we are. At the bottom of page 159 in table 3-9, it says estimates for the ultimate strength in shear. And it says for malleable iron and copper alloy. So this is a copper alloy because it was a beryllium copper and it's hard. And by the way, those are the properties for the hard version of it. Anyway, it says that the ultimate shear strength for this material is 90% of the ultimate strength. Now this ultimate strength would be a strength measured just in tension. It would be the normal stress or normal strength of the material. This would be the strength of the material in shear if it's a copper alloy according to this table. But then you notice that it says see table 3-8 just above for guidelines for design factors when ductile materials are used. So if you go over to the ductile materials, you'll see that for repeated loads, which is what we've got described here, what's been described is that the shear stress, the design shear stress, should be the yield divided by 8. And so we're in somewhat of a quandary about which one to use because 4% elongation is pretty close to our cutoff of 5. On the other hand, it's below. And so what do you do here? Well, I wrote a note in my solution that you can look at and read, and basically my reasoning goes like this. If I use the ultimate strength, I can take 90% of that strength and get the ultimate shear strength. The only problem with that is that I don't like that because the number I get here would be larger than 1,000. Now if I use a design factor that's greater than the one for ductile materials, then I need a number larger than 8. So say 10, I don't know. We could use something. The point is that I'm still going to effectively end up with about the same design stress. So I decided, forget all this, we're close to a ductile material. I will simply use the yield strength over 8 and get about what I would, say if I used a design factor of 10 with 90% of the ultimate strength. And so that's what I chose to do. Now, right, wrong, There's one problem here. First of all, this yield strength is usually a yield strength that is a normal stress. And so since I don't remember Moore's circle all that well right at this point, and in this chapter you wouldn't understand it anyway, this may not be a terribly precise analysis, but for our purposes and to illustrate calculations here, it should be fine. So we'll just continue with this. Alright, so that's what I'm going to use, and basically the shear strength would be equal, or the shear stress would be equal to the force divided by the area. So the area we're talking about, let me expand this just a little bit, the area we're talking about is whatever area we end up with from designing the diameter of this pin. Okay, so that's the area we're talking about, and the force we're talking about is just this load P. So this is just P times the area of a circle, pi over 4d squared. Okay? Now, like I said, I'm going to set the design stress equal to the yield strength over 8. And so, solving for the required diameter of the pin, I would have the square root of 4p over pi 8 over the yield strength. Plugging in all the numbers, 4 times 10.2558 kilonewtons multiplied by 8 here, divided by pi and divided by the yield strength. Well, the yield strength is 1,000 megapascals. I plugged that in as a gigapascal because I know a gigapascal is a kilonewton per millimeter squared. Kilonewtons cancel. I'll be left then effectively with the diameter in millimeters. When you plug that into your calculator, what you'll find is that this is about 10.22 millimeters of required diameter. Okay, well, you don't want to specify a pin that size. You can't get one that size. That's the standard. You'd have to have it turned, and that's expensive. So you go up to the next basic size, and I'd recommend not going to the secondary basic sizes, but the primary. I forgot what they're called. But anyway, they're in your book. And this is also a page you should probably bookmark, so let's go to it. Let's see. It's at the beginning of the appendix. And let's see. The page number, here we are, is page 692. Table A-2, preferred basic sizes. They're first and second, that's their name. So the first preferred basic size above 10 is 12 millimeters. The second is 11, so I'm going to go with 12, mainly because I know that I probably would have trouble finding a pin that's 11 millimeters in diameter. So I went ahead and just said, well, specify then the diameter of the pin as 12 millimeters. Now at this point, if you look at the figure that was drawn, you'll realize there's a slight problem, because if that thing's to scale, we need more material around that center part. We're going to need a whole lot more material in this area in order to get a pin of 12 millimeters in it. So what happened? Well, there's a couple things that could have happened. It could be that I'm not thinking about this right, and I've way over-specified the design or the diameter of the pin. It could be also the fact that we're using a copper pin here that can't take very much shear stress. And maybe that's just something we have to do. Maybe we have to increase the size of this link, whatever it's made from, just so that we have enough room to put the pin in. Now, it's also possible that the strength of the pin is very, very low, although that doesn't look terribly low. That's, 1.3 gigapascals or so. So it could be that it's very low, and we just don't need much material around it if that other link is, if the link, I mean, is made of steel. I don't know. It doesn't matter too much. We weren't actually told the precise shape of the link, and so it could be that it's actually much larger than what what it looks like in the figure. Anyway, so there's the diameter that I specified, but there's actually another way that this pin could fail. This pin could fail by the surface being deformed. If you imagine the bearing surface, basically, so if you have the pin, something like this, there's basically force being applied from the link onto the pin, and that surface force, that surface stress, could cause failure. So even though it's not asked for in the problem statement, it's a good exercise to go ahead and solve this part as well. So that's what I'll approach next. So let's consider not just the shearing, but also the bearing load. Okay, so I'm going to assume that the pin is close fitting, and if that's the case, there's a few guidelines in your book about that. Let's see, it's before the shear section. Let's turn back to it. Yeah, here we are. Page 147 and 149 essentially. Bearing stress, equation 320. Bearing stress is computed in a similar manner to direct normal stress. The bearing stress is the force over the bearing area, but you have to be careful because the bearing area is something you have to consider. In fact, on the next page, in fact, 2 pages, 149, about in the middle it says the effective bearing area for the cylindrical pin in a close-fitting hole requires that the projected area be used, computed as the product of the diameter d of the pin and the length L of the surface in contact. Now, what is that talking about? Well, if you look at a pin, the pin of course has a diameter, but it also has a length. So essentially you're talking about a projected area. It's this rectangular area that's projected that is being used to calculate the bearing stress area. There's a reason for that. I won't go into it. It's essentially the fact that if it's a close-fitting pin, there's pressure all around the outside, and so that pressure has a varying angle, and so you take the vector components, you end up with effectively an area that is that cross-sectional area. But for our purposes, the bearing area is simply the diameter times the length. Now, if we go back to our problem, since the bearing stress is equal to force over the bearing area, then the load that's being applied again is just this 10.2558 kilonewtons divided by the bearing area. Well, the bearing area is just d times L. Now, notice what we're really interested in here, and I'm sorry, I use the term T for thickness, because the length of the pin is going to be equal to the thickness. So, well, not equal, of course, it'll be longer, but the bearing area along the pin will be equal to the thickness of the length. So I used T here. And what that allows me to do is solve for the thickness. The thickness then is the load P divided by the diameter D. And what I'll need here in rearranging this is the, let's see, I've got to move the stress down, but I'll need a design stress to work with here. So let's figure out what the design stress should be, and then actually I'll come back to this and solve it. Now, we've determined that the pin is a brittle material. There are some recommendations for brittle materials subjected to normal stress like this, because the normal stress is going to be stress at the surface that's normal to the surface. That's why it's called normal stress. Anyway, in your book, early on in the chapter 3, your author gave a table where he suggested design factors. Here we are, page 119, table 3-2. Now this is a repeated load, recall. And he has 2 columns here, one for ductile, one for brittle. Well, now we can just use the brittle material, which is on the right-hand side. Under repeated load, you'll notice that the design normal stress, sigma sub d, is equal to the ultimate strength of the material divided by 10. So that's the recommendation. So now we finally get to use this ultimate strength of that material. So basically we'd set this equal to the ultimate strength over 10. Solving for the thickness then, we'd find that the thickness is P over D multiplied by 10 over SU. So this is a pretty simple, straightforward thing. I guess I should have put that somewhere else. So anyway, continuing, the thickness T from here would be the load P, 10.2558 kilonewtons times 10 divided by the diameter of the pin. Well, we've sized the diameter of the pin. We made it 12 millimeters. So let's plug that in, 12 millimeters. And divided by, where are we? The ultimate strength, which is 1.344 gigapascals. Again, I'm just converting to gigapascals immediately instead of megapascals so that it plays nicely with kilonewtons. Okay? And of course we'll end up with a thickness in millimeters. When you plug this in your calculator, you get about 6.36 millimeters. So I went ahead and specified a thickness of 7 millimeters. Now that's not a first but a second preferred size. The reason I did that is because this probably would not actually be the specification. 7 millimeters is not all that thick. 7 millimeters, 8 millimeters is about 1/4 of an inch or so, if I remember right, if I'm thinking straight right now. Anyway, 7 millimeters is not terribly thick, so it's possible that this could be made out of sheet metal, which follows gauge sizes, or it could be made out of stock steel. And in the United States, you're going to get that in inch units. And so I just left it here to make it close to what I actually wanted, assuming that later on I would choose a particular sheet material for this to be made from and be constrained on the thicknesses that are available. So anyway, there's the thickness that I specified for this problem. So notice that this pin should be able to resist both shearing stresses and bearing stresses.